few more examples of log and exponential equations. And then, time permitting, we're going to do something I hope will be a little special. We'll get to that. Once again, we have these laws of logs that we really need to be very intimate with. Log of a plus b, log of a plus log of b is log of a plus b. Adding logs is like multiplying. Subtracting is like dividing. And if I have log of a to the b power, that's just b times log of a. That is, exponentiation becomes multiplication. So let's look at a somewhat more difficult problem in this category. Okay, well, we really have an equation here. Suddenly we can't really evaluate these logs, not directly, but we can use our laws of logs to try and accumulate these x's in the same place, because that's a good strategy. So, see, log of x squared plus 1 is, of course, log of x minus 2 times x plus 3. Well, recall that the log function is a one-to-one function. So we can immediately jump to the fact that x squared plus 1 must be equal to x minus 2 times x plus 3. Another way we could do this is whatever base we happen to have here, we could raise both of these to that base. Thus we would have f inverse of f of x is equal to x, meaning we get rid of the log that way.
Question.
Yes?
So if you say you divided it by the log of that base, would it still disappear that one? So like if you divided both sides by log, then you would still have the same thing.
You divided both sides by a log. I don't. I divided both sides by log of. Oh, okay. I'm not sure if this is where you were going, but if it is, it's a very dark alley. The word log is just a description of the function. I'm not multiplying log times this. I'm applying the log function to this. So while it looks like I can just erase log here, which I can, you want to be very careful about that. If you thought you could do that, you might think you could do this. You might think, oh, using that logic, and that would be very wrong. Okay? So, was that where you were going with this? When you said, can you just divide? Okay. All right. Well, must be a little careful. Okay, we're not done, and there's something new here, or something we've seen something like this before. Let's go through. X squared plus 1 equals x squared minus 2 plus 3x plus x minus, I think there is. Okay, the x squareds cancel, and we get, I'm just going to add 6 to both sides, so I'm going to get x equals 7. Well, we need to check this, because just because we end up with an x here that seems to work, sometimes in the process we pick up something that isn't valid. I think we saw that on Friday. You could end up trying to take the log of a negative number, which doesn't really work. All right, so let's plug it in. We have log of 49 plus 1, or 50, equals log of 5 plus log of 10. Well, that's just fine, right? Clearly, log of 50 is log of 5 times 10, so we're good. All right. Recalling that if I had something like this, x equals 8, I can write it as the, using the inverse functions. I can just say, well, this is the log to the base e of x. So an equivalent statement is e to the exponent equals, did I do that right? Yeah, I did. Equals x. Again, e, unstated here, e is the base. All right, the other way to get there, of course, is I could always raise log of x to e, do the same thing over here, and then realize that this is just applying a function and its inverse. So I'm just going to get x again. All right, well, let's find a use for that. If I had this problem, log to the base 2 of 25 minus x equals 3. Well, how am I going to rewrite that? Let's start with the base. What's the base here?
2.
2. Okay, what am I going to raise that to?
3.
Okay. And what else is left? 25 minus x. So this, of course, is 8. So let me subtract 8 from both sides and add x. Again, I want to check these. The log to the base 2 of 25 minus 17 is 8. But what's that? That's, of course, 3. Because 2 cubed is 8. All right. right. This up for the moment. Sometimes you have a problem like this, but you don't have it in front of you right away. You have to do a little work, but it's work you're used to, right? So, for example, if I said 4 plus 3 log 2x equals 16, well, I don't have my log where I want it yet, but it's not hard to get it there, right? I'm going to subtract 4 from both sides. Just like I do with any other algebraic equation, I can divide by 3. I left out, I want this to be log to the base 10. So now, okay, I have 10 to the 4th equals 2x. This is 10,000, so of course my x is just 5,000. Once again, if I plug this in, 5,000 times 2 is 10,000. So log to the base 10 is 4. 3 times 4 is 12, plus 4 is 16. So that still works. I know that this is a little tedious. We're just going over some problems. There's a few more, but in each one I'm trying to kind of give you insight into the kind of issue you might run into when you're doing these. The last problem we're going to do in a minute or two, you're going to see that we're going to run out of room here. These methods aren't going to work, but yet we still can go forward. Let's see. Let's see what else. Okay. All right, one more kind of straightforward problem. Well, almost straightforward. Let's take this, look, log to the base 10 of x plus 2 plus log to the base 10 of x minus 1 equals 1. Okay, there's something obvious to do here. We use our law of logs, and this becomes x plus 2 times x minus 1 equals 1. And again, we unravel this using the inverse function, and we find that x plus 2 times x minus 1 equals 10 to the 1, or 10. You know, now this should be straightforward, right? X squared plus 2x minus x is plus x plus 2 equals 10. So we get x squared plus x minus 8 equals 0. Doesn't seem right.
Should be minus 2.
Thank you. Okay, so that looks a little better. So that's going to be x, 3, and 4, all right? So plus 4 minus 3 equals 0. So x equals minus 4 and 3. This is why we have to check. try 3 first. It says log to the base 10 of 3 plus 2 is 5, plus log to the base 10 of 3 minus 1 is 2, right? Equals 1. That's just log to the base 10 of 10 is equal to 1. Good. When we try minus 4, we see this is log to the base 10 of minus 2 plus log to the base 10 of minus 5. You could make a very simple and understandable mistake of thinking log to the base 10 of minus 2 plus log to the base 10 of minus 5 is log to the base 10 of minus 2 times 5 minus 5. I mean, that's why it comes out as a solution. But there's an obvious problem here. Log to the base 10, log to any base of minus 2 and minus 5 are undefined. So this is just kind of a phantom root. Yes, Carlos.
They're defined because they're negative?
That's right. They're not in the domain of the log function. Everyone clear on that? You don't want to solve one of these and get a value and then find out it doesn't make sense. And that's the problem here. That's why I encourage you to always check. Okay. Finally, we come across something that is pretty hard. Say x squared equals 2 natural log of x plus 2. So, we're brave. We go forth with our mathematical swords and we say, let's give this a try anyway. Of course, I want to divide both sides by 2. And now I want to get rid of this log here, right? This natural log. So I'm going to raise both sides to the power of e. This side, that's fine, e to the x squared over 2. And this side, that's just x plus 2. And I look at that and I go, yeah, I don't really know what to do with that, do I?
We divide by e.
Well, this is x squared divided by 2 to the power of e, right? So dividing this side by e, well, dividing this side by e, I get that, which is fine.
Divided by e,
But this would just be minus 1.
divided by e gets rid of the natural log, right? That's what we did.
Here?
Yeah.
No, it's not dividing by e. It's taking the function and its inverse. All right, so think of it this way. Think of f of x equals the log of x. F inverse of x is e to the x. These are inverses. So when I take f inverse of x, right, f inverse of f of x, that's exactly e to the log of x. which by our, property of inverses is just x. Take a function, you apply it, and then you take the inverse function and apply it to the result. You get back what you started with. That's what an inverse function does. You might want to call it a reverse function, right? It kind of reverses what you did. Okay, so we're kind of scratching our heads here what to do with this. It turns out that, at least at this level, there's nothing we can do with it, except we might be able to actually come up with some kind of approximate answer. And let's kind of think about how that might work. Let's take these two functions here. Let's graph them. This one's the hard one to graph. At 0, this is 1. There's something I notice about this function, right? F of x equals e to the x squared over 2. If I look at f of minus x, that's e to the minus x squared over 2. But that's just e to the x squared over 2. Now what's that? What does that tell me? It tells me two things, right? First, I've categorized this function. It's what kind of function? It's something you will need to know on the exam. What kind of function have I just described here? I've just shown that f of x equals f of minus x. We have a name for that. Okay, I couldn't quite hear.
Inverse function?
It's not an inverse function, but that's a good guess. Better guess? It's an even function. This is the definition of an even function. What's an odd function? F of minus x equals what? Yes?
Negative f of x.
Negative f of x. Okay, so that's the first good thing. We know this is an even function. What do I know about the graph of an even function? Okay, it's the same on both sides. Both sides of what?
The y-axis.
The y-axis, thank you. Both of you. Whatever's on this side, it'll be reflected on this side. So I really only have to, for the moment, worry about one side. So let me go ahead and do that. Let me plot a few points. So if I plot 1, that's a half. E to the 1/2 is the square root of e. E is 2.7 something, so what's the square root? I mean, you have a calculator, so, but let's say 1.5, that squared is 2.25. It's got to be a little bigger than that. 1.6 would be 256. A little bigger than that. 1.7. I can't do that in my head, can I? 289. Okay, so it's between 1.6 and 1.7. Okay, so 1.6 and 1.7. Forget that. Okay, what about 2? Oh, that's really easy. That's just E. 1.7. I don't really think I'm going to be able to figure out the solution with my ugly, graph here. But I want to at least see what's going on. All right, it kind of looks, this is exponential, clearly very exponential. I've got something like that. And now I have, on this side, the function y equals x plus 2. Well, that goes to the y-intercept 2, and it has a slope of 1. Aha. Well, that suggests to me that this equation will have two solutions. One of them down here, maybe between -0 and -1, and one of them up here, I don't know, 3 or 4. I could get like really nice graph paper, and I could get a straight edge, and I could graph very carefully, and I could actually come up with some kind of approximate value. But we don't do that anymore, because we live, we don't have to survive with sticks and stones, right, anymore. What would be a good strategy to find this using, say, our TI calculator? Well, the one I like is, let's make this into one function. Let's say f of x equals, I'm just going to subtract x plus 2 from both sides. Equals x squared over 2 minus x plus 2. We can plug that in, and then all we have to do is ask our TI, where are the zeros, right? Because anything that makes this 0 is going to solve this. All right. We did that. And my TI tells me it's minus 0.7117437, something else, approximately. I don't have what we call a closed form solution. I don't have something with just functions. And the other solution is 1.600706. So we can solve these. I hate to just give away the ghost here. Can't really ask you to solve this on an exam, can I? Not everyone has a TI calculator, and we don't even know if we want to let you use those this period. So, okay, so we can get some kind of answer. Not as satisfying as something in closed form, but we can get something. Okay. One more practical problem. All of you business majors and economists out there will love this one. And if you ever have to work for, if you're ever a computer programmer, and you have to work for some business type person, this will be good to do too, good to know. Okay. I don't know why, but the problem starts off, you have $5,000, which is totally irrelevant. Doesn't matter. See why. We have, that's our principal, or our starting principal. The interest rate is 5%. Of course, we write 0.05. And we want to know how long will it take at this interest rate to double our money. right? Kind of like you go to a casino, double or nothing, right? Except there's no nothing here. We're going to double it. And we ask this question in two contexts: compounded semi-annually. That's twice a year. That's kind of the A part. And the B part is continuously. Right. It's really two different problems, but we'll go at them one at a time. So for the first problem, we need some kind of equation for our future principal. That's going to be our current principal times 1 plus our interest rate. We're compounding semi-annually twice a year. So what do we want to divide this by?
6.
6?
Yeah.
By 6.
Because there's 12 months in a year, and then you're doing it twice, so 6 times 2.
This is the interest rate, the yearly interest rate for 12 months.
And this is semi-annual, so it's 6.
So
Right?
if this was the interest rate for a month, then I'd multiply it by 6, right? Right? For 6 months. Right? If this is the yearly interest rate, what's the monthly interest rate? Don't be frightened. What? Carlos?
Would you divide by 12?
Divide by 12. You're on the right track, but okay. So this is the monthly, and now I want semi-annually. I'm going to multiply this by 6. Yeah. Okay. But that's why this just becomes 0.05 divided by 2. Okay? Make sense? All right. Okay, so now there's my time period in years, but I have to multiply that by, I'm sorry, that's my time period in semi-annuals. Yeah, but I have to multiply that by 2. Okay. I happen to know these values. As I said, this is 5,000, and since I want to double my money, this is 10,000, but I don't really need that. All I really need is EFT P0. Because what does this have to be? I want to double my money. That means my future is double, right? So this is just equal to 2. All right, now I have something I've been working on, right? It's just an exponential kind of thing. What should I do to solve this? I want to know what T is. I want to know how many 6-month periods it's going to take. I know it's a different context now. It's money. It turns people off. plus 0.025 raised to 2x equals 2. 1.025 2x equals 2. What do I want to do now? Try something easier. What if I said 5 to the x equals 2? What would I do with that? Yes?
You take the log of both sides.
Okay. Sounds good. Now, does it matter? What base do I really want to use?
10.
Okay. I was thinking 5, because then I just get x, but you know what? I don't have a log to the base 5 on my calculator, so, you know, this is going to work better if I actually, this is kind of a real world problem, so yeah. Okay, so what do I do with this? Oh, I erased my logs. What do I do with this? I don't like that x up there, do I? I want to get it somewhere I can handle it.
Make it a coefficient.
And just move it over here. That's what you meant, of course. Yeah. So I have x log to the base 10 of 5 equals log to the base 10 of 2, or x equals log to the base 10 of 2 log to the base 10 of 5. And that I can plug into my calculator. I mean, it's an exact number right now, but I can get some kind of value for that. Okay, but that was just one of the problems. The other problem was how long does it take continuously? That's a different equation. It's actually easier, right? I mean, I want my PF of time equal to E0, e to the, what, t? And again, I want PF of t over P naught. I want that to equal 2. So I'm just left with e to the t. Now t is in years, right? And how would I find the solution to this?
Natural log of both sides.
Yeah. Just take the natural log. So now I just get t equals the natural log of 2. All right. Questions on logs, exponential functions, equations with logs and exponential functions. Okay, that's where the exam is gonna, the material you need to know the exam is ending. We're gonna start working on trigonometry. Trigonometry will all flow over to the final. So, I have on my website, under handouts, a sheet that says, here are all the things that, new things we've covered that you need to know. previous handout is also there, so you could look at things from the very beginning of the year. Some of you might want to review those too. Anything could be on the exam, but it'll mostly be on what we've done since. Right? Okay. I'm experimenting a little here. I want to try something. You could think of this as for entertainment purposes, if you like. I think most people would, in your position, would find this entertaining, especially given where this course has been. We've covered a number of things that I'm just going to jot some of them down. Complex numbers, polynomials, exponential functions. And we're going to cover trigonometric functions. Who here has never heard of a sine or a cosine? I mean, good. Okay, everyone's at least heard of them. I left a little room here. Has anyone heard of something called a hyperbolic function? That when I wrote it, is that a yes?
Mm-hmm.
You've heard of it, good. Okay. Most of you have, you've heard of it? Okay, yeah. Trigonometric and hyperbolic functions. I'm going to show you what they are. It's not really a big deal. It sounds really like a big deal. They're very related, and we'll see how. But all these things are, they just seem like a grab bag. You start the class, you learn one thing, you learn the other, and all these things are necessary in your preparation if you want to take calculus. They're also, it's good math, but it'd be nice to know that this isn't just we just threw a bunch of subjects into a can and shook it up, and now we're making you learn all this. These things are very interrelated, and unfortunately, you don't really get to see that as part of the course. But I want you to kind of see that, because to me, this is where mathematics gets really gets exciting. I know I don't seem excited yet, but I'm getting there. The first thing I have to show you, though, is something I can't develop for you yet. You really need calculus to develop this, so I'm just gonna state it. We have this function e to the x. It's in the category of hyperbolic trigonometric functions in that it's called a transcendental function. And by that we mean you cannot describe e to the x just in terms of a finite polynomial. In other words, a x to the n plus, we'll say an minus 1, x to the n minus 1, all the way up to a sub 0. You can't do it. You can approximate it, but you cannot replace one with the other. However, you can surprisingly replace it with an infinite polynomial. In fact, the infinite polynomial you can replace it with, this is a summation sign. So if I go from k equals 0 to infinity, the sum of x to the k over k factorial. Does everyone know factorial function? Anyone not know factorial function? It's easy. Everybody knows that. So what this looks like is x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial, and so forth. Now, I'm sure all of you know what x to the 0 is, right? What is x to the 0? It's 1. So let's just replace that. Anybody know what 0 factorial is? Yeah. Yeah, 0 factorial is 1. That's very strange. There are stranger things. Okay. Let's check this out, just to make it seem plausible. If I were to plug in 0, e to the 0, that would, of course, equal 1. But what does it equal in this sum? It equals 1 plus 0 over 1 plus 0 over 2 factorial plus a bunch of zeros. Yeah, okay. So we have one value that seems to work. How about, let's just try one more. E to the 1 equals what? That would be 1 plus, well, that's 1 over 1 factorial, that's 1. Plus 1 over 2 factorial, that's a half. 3 factorial is a sixth. Fourth, right, like that. Well, let's see, what is that? That's 2. That's 0.5. Sixth is, you know what a sixth is? Decimal of 6. Six divided into 1. 6, 4, 6. 6 is 1.6. We're just doing approximations. 1/24th, that's almost a 25th. It's 0.04. So what do we get here? 6, 0, and that can't be. I wrote that wrong. 1, 6, 6, 0, 4. I'm just, approximating here. 6, 2.66. All right. No, it's 7. 2.706.
Thank you.
2.706. Yeah, well, E is actually 2.71828. I'm getting there. I'm getting there in this sequence. Okay, so what? Right, well, before this gets real exciting, I have to take a slight diversion, and I have to tell you about what the hyperbolic functions look like. Hyperbolic functions. So we have something called the hyperbolic sine, which we write like this, but with an h. And we define that as e to the x minus e to the minus x over 2. And we have another nice function called the hyperbolic cosine of h, which we define as e to the x plus e to the minus x over 2. A nice thing about writing them this way is if you do a little work, you can see immediately something kind of cool. You can see that if you plug in minus x here, well, this becomes minus x and this becomes plus x. It stays the same, so therefore it is a blank function. Even. the exact opposite happens here. You get an odd function, and though you may not have run into this in your previous life where you learned sines and cosines, the sine of x is an odd function, and the cosine of x is an even function. So there's already kind of a connection growing there. But let's use this formula here we have for e to the x. All right. I already have e to the x written here. What's e to the minus x? Well, that's going to be 1 plus minus x over 1 factorial plus, oh, the minuses here cancel, so it's just x squared 2 factorial. X cubed, I'm going to get a minus 3 factorial, and so forth. Let's look at the cosine function first. I'm going to add these two. So all the odd terms drop out. All the even terms appear twice. But since I divide by 2, they're only going to appear once. So this is 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. Oh. So now I have, have an expression for this function. And what's going to happen here is just the opposite. All the all the even function, even terms, even exponents are going to drop out. And I'm just going to get x over 1 plus x cubed over 3 factorial plus x to the 5 factorial. Okay. It's nice. I know what these things are. I know how to write them as an infinite polynomial. Kind of connected polynomials, exponential functions, symbolic functions. I haven't done anything with complex numbers yet, but we'll get there. All right. Once again, I have to make a little jump here. I have to just tell you something. But at this point, maybe it even sounds plausible. There's a similar way to write, from the sine and the cosine function. There's a similar way to write the hyperbolic sine and cosine. There's a similar way to write the sine and cosine. Sine of x is equal to, looks very similar. It's x over 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. It's the same sequence except every other term is a minus. Same thing over here. 1 minus x squared over 2 factorial, x to the 4th, 4 factorial, minus x to the 6th over 6 factorial. A nice feature here is you can look at these expressions and see immediately that these have to be odd or even functions. Everything over here, every x is square, to some power of 2, which means that minus x disappears when you plug it in, so it's an even function. And here, you always get one more factor of x, so it's going to be an odd function. All right. Here's where it gets interesting. What if I was to plug in, instead of x, e times ix? I wonder what happens. Well, I get 1 over 1 again. Now, here I get x, but I get ix for 1 factorial. Here I get 2 i's. 2 i's is minus 1, so it's just minus x squared over 2 factorial. The next term I have 3 i's. Well, that's minus I times x cubed over 3 factorial. And finally, when I get around to 4, 4 i's is just 1, so x to the 4th, 4 factorial. And that pattern continues on. But I could separate these out. I could separate the terms with I and without I. Right? We get 1 over 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And then I could also, take out a factor of I from these other terms. Right? That would be x over 1 factorial plus minus x cubed over 3 factorial plus x to the 5th over 5. But I've seen these before somewhere. I saw them over here. This is just this sequence. This is just the sequence. So I could rewrite e to the ix as cosine of x plus I sine of x. That's quite astonishing. This is a very famous, important formula. It's known as Euler's formula. Euler, a very important mathematician who lived in the 1700s. And there's kind of one neat thing that everybody likes to do with this. You have to realize these x's here, they're not in degrees, they're something called radians. If you haven't heard of radians before, that's okay, we're going to be doing that very soon. But what you need to know is that pi radians is 180 degrees. And if I plug in here e to the I pi, I get cosine of pi. Cosine of 180 degrees turns out to be minus 1. Sine of 180 degrees, sine of pi, turns out to be 0. That's it. E to the I pi equals negative 1, or as we like to sometimes write it, e to the I pi plus 1 equals 0. This is called Euler's identity. Has anyone seen this before? It's kind of neat. I mean, it connects complex numbers, exponential functions, and trig functions all in one. Well, the formula does. All right. Okay, about 2 minutes left. There are 2 more things I want to point out. One is just that we end up with 2 kind of astonishing formulas for sine x and cosine of x. Sine of x turns out to be e raised to the ix minus e raised to the minus ix. Kind of looks a lot like a hyperbolic formula. And cosine of x is e to the ix plus e to the minus ix. All right, I had something else neat. You can look at my notes. I'm going to let everybody go. Thank you. I hope you're at least a little excited about learning about trig.